In this tutoring film, the electrical and machinery course ELE 361 has some lecture slides, and this is a solution for an example from the lecture slides, slide number 201. What's the problem? Let's look at it. It says a separately excited DC motor drives the load at 1150 revolutions per minute. So this is the equivalent circuit of the motor. Motor is here and it's driving a mechanical load, and its field windings are excited by a separate voltage source V sub F. Part A asks, find the gross output power, electromechanical power output produced by the DC motor. Part B asks, if the speed control is to be achieved by armature voltage control and the new operating condition is given by 1000 RPM speed and torque is 30 Newton meters, then we have to find the new terminal voltage Vt prime, while Vf flux F is kept constant. So this is a kind of motor control circuit. This is the handwriting of the same problem on the classroom whiteboard. Everything is as indicated. So terminal voltage is varied to control the speed of the motor. The question in the part B of the question, it asks the new terminal voltage to reduce the speed to 1000 RPM while supplying 30 Newton meter torque to the load. First, let's understand what's happening in this problem. This is our equivalent circuit. This is the same circuit in the previous slides. The field winding creates field flux through the while via the field current I sub F, and armature is receiving, and armature coils are excited and force and so as torque is produced here in the armature. So in the air gap, flux is observed, and stator and rotor fluxes create the torque. Thus torque is generated according to the theory given in the slides. This theory states that rotor and stator torques act to create that torque. In the ideal case, the mechanical output power, which is torque times speed actually, so let's replace this by omega. There's a little mistake here. Torque times speed equals to electrical power input, which is the voltage across the armature and the armature current in the circuit. So we give some electrical power into the field to this motor. That power is field voltage times field current, but it's not specified in the problem. We do have main electrical power is given through the armature terminals or main terminals of the motor. Some power is lost in the armature resistance. This power is calculated to be 480 watts because we know the armature current and this resistance, and power is transferred at this point across the armature to the mechanical power. So net mechanical, all mechanical power, gross mechanical power, is net mechanical power output plus losses. So there is a power transfer from the electrical side to the mechanical side along this axis. This power, electrical power input to the system, is E sub A, I sub A, and Vt minus, that we substitute Vt minus Ia Ra into Ea and write Ia. So Vt times Ia minus that power loss on the resistor results in 4.02 kilowatts at this point. So the electrical power input to the system is 4.5 kilowatts because we know the terminal voltage and current, and some power is lost here. Net power converted towards mechanical is 4.02 kilowatts in this motor. In part B, we change the terminal voltage to change the speed of the motor. So after changing V sub A, which is almost equal to terminal voltage, neglecting the voltage drop across the armature resistance, the new operating conditions became new speed 1000 RPMs, new torque 30 newtons per meter. So we have to find the new terminal voltage, while field is kept constant. So these are the this is the set of the initial conditions. Initial condition means before the speed control. In part A, terminal voltage was 125 volts. EA is from that value we deduct the voltage drop across the armature resistance, which is 111.68 volts. Rotational speed is 1150 RPMs. Torque is not specified in the first part, and field flux again not specified. In part B, after speed control, the terminal voltage is asked, so all the primes reflect the after speed control condition. EA prime equals to EA times the speed ratio. We know that the induced EMF is proportional to the speed, so by taking the ratios we can calculate the new EA prime. N prime is given 1000 in the problem, torque is given, and field flux not specified but not critical, it's held constant in these two conditions. So we know that from E sub A equals to proportional to the field flux times speed, we may find that constant, because this is geometrical constant, and in the question it's mentioned that field is also kept constant. So omega m here is EA over that constant. So we calculate the speed in terms of radians per second from RPM value. So this value is 120.43 radians per second. This is the new condition speed. Sorry, this is the general condition for the initial condition. So this is the first speed. In the first situation, this constant is 0.0927. So that's again constant for the second case. Since we know EA prime, we can calculate new speed. So we substitute this value instead of that constant. So the new speed in the problem is this. Well, we know that it's already given in the problem, but we are checking ourselves whether we find the correct number, etc. So for the second situation, let's also check whether our calculation is correct or not. For the new speed, this should be primed, of course, and this speed in terms of RPMs is 999.5, which is almost equals to 1000 RPM. So check complete. So this says 0.5% error with the given parameters in the question. So that means our approach is consistent and right. So we will use that constant K times phi, geometrical constant and field flux of 0.927 for the new armature current calculation. The torque in the second case is directly proportional with the armature current, with the same constant. So we substitute this to calculate the new armature current, and torque in the second part, well, in the question torque is given with capital T. Here I represent tau, so you may assume they are both the same quantities. 30 Newton meter is the next torque, so armature current is calculated to be 32.36 amperes. As a result, we substitute the values only for the armature side. Of course, we have to add field with some voltage source, etc., adjusting, but it's not critical. So this is the terminal voltage, and of course it should be primed for everything. Yeah, we do have armature current of 32.36 amperes across 0.37 ohm resistor, which results in voltage drop of 1197 volts. So this is substituted here, and from the speed ratio we had calculated the induced voltage as 97.11 volts, and we substitute there. So we end up with new terminal voltage is 109.1 volts. So this concludes the solution of our problem given in the lecture slides and in the lecture notes.